Okay, so now moving beyond the Euclidean setting of part one of these comments, video notes, um, we're now just considering a Riemannian manifold without any fixed embedding into Euclidean space, okay? And a Riemannian manifold, we can use the metric to induce a distance function, okay? So first we construct we construct an arc length function which measures the arc length of a curve, and we just integrate. If you take a curve which is parameterized on some interval, then the length of that curve is given by the integral over the parameterization of the norm of the derivative of that curve with respect to the parameterization, and you integrate over the parameterization. Okay, so that's the length of the curve. And the norm is now defined using the Riemannian metric. So the norm of a vector v is going to be the square root of g of v comma v. All right. So this allows us to measure lengths of curves, and it's an important fact that the length of a curve is independent of the choice of parameterization. Now, technically speaking, the lecture notes that I'm using, I'll post the name of the professor who's writing these lecture notes in the description. But we need to assume a regular parameterization of this curve. So we want this curve to be an immersed one-dimensional submanifold of our manifold, which means that we need the derivative to be non-zero with respect to the parameterization. So the speed of the curve is always strictly positive, okay? Right, so now with that additional assumption, it's called a regular parameterization. And the length of the curve is independent of a regular parameterization. So this is a useful exercise in the change of variables theorem, and I'll leave that exercise to you. But it turns out there's a more general statement, which is that if you have a local isometry, let's say phi, from a Riemannian manifold M to a Riemannian manifold N, then this local isometry preserves the length of curves. In the sense that if you have a curve gamma in your manifold M in your domain, then the length of gamma in M is equal to the length of phi of gamma in N. Okay? Now, among all parameterizations, there is a kind of a parameterization which is very important called the arc length parameterization. And the way that it's constructed is you essentially define the arc length function to be this integral from 0 or from a. If you have a, you basically integrate over you do the cumulative integral um, of the norm of gamma prime, norm evaluated with respect to the Riemannian metric, of course, and it's the cumulative integral from the start point of your interval of your parameterization um, to some variable endpoint t, and that gives you the arc length function s of t. Okay, and so this is a strictly increasing function because again the we're assuming a regular parameterization, so the speed is strictly positive. So the arc length function is strictly increasing, and therefore you can find an inverse and use the inverse function theorem. And in particular, the inverse function theorem will allow you to show that the norm of gamma prime, when gamma is parameterized according to its arc length, then it's the norm of the gamma prime is identically equal to 1. So the tangent vector to the curve has constant length 1. Okay? All right, and this is called a normal curve. A curve with constant speed is called, shockingly, a curve with constant speed. An important side note that these lecture notes make is that if you have a one-dimensional Riemannian manifold, then if you take a point, the local neighborhood of that point is a curve, and you can use arc length as a coordinate. And with respect to that coordinate system, the metric tensor is just the identity, or the component of the metric tensor is just 1. And so G is just ds tensor ds, which gives you an isometry, a local isometry between any two one-dimensional Riemannian manifolds. So that's an important fact, is that any two one-dimensional Riemannian manifolds are locally isometric. Now, if you have a piecewise C1 curve in the manifold, then you can define its arc length by summing over the arc length of all the pieces. Let's see, I'm just following the notes here. I'm covering these so that I can just review this later. These are lecture 3 of Professor Wang's lecture notes on differential geometry. So finally, we get to the notion of a distance. So as I kind of discussed in my video defining the length space, this is kind of a similar idea at work here. So we can define a metric, a true metric, not the metric tensor, but an actual distance function on the manifold called the Riemannian distance using a variational principle, where we define the distance between 2 points P and Q on the manifold to be the infimum over the length of all curves which connect those 2 points. All right, and this variational principle, you can kind of compute the first order perturbation, the first order condition for optimality, and that'll give you something called the geodesic equations. All right. So, but you need, you need some coordinate system to start doing that sort of variational calculus. You need to be able to do calculations in local coordinates in order to kind of solve for the coordinate form of the geodesic equations. But you can prove like existence and characterization properties, I think, outside of coordinates. I don't know. We haven't got there yet in the course, so I don't want to get ahead of myself. Okay, so so now there's an important step to showing that this is a distance function, namely showing that the distance between um, two distinct points is greater than 0. So the proof technique to show, so all the other aspects of this distance functional, which is the infimum over the distance between P and Q, is the infimum of the arc length of all curves connecting P and Q. All axioms of the distance functional are somewhat straightforward to show, except for the positive definite axiom. So in particular, if 2 points are distinct, um, then their distance is strictly greater than 0. And so to show that, you need to use the fact that the manifold is Hausdorff. And so consider 2 points P and Q, which are not equal. Since the manifold is Hausdorff, you can find a neighborhood of P such that Q does not belong to that neighborhood. Okay. Now you choose a coordinate chart contained within that neighborhood, which sends some open set U of P to the unit ball in Euclidean space. And now consider the subset of the unit ball in Euclidean space, namely the compact ball of radius 1/2 sitting inside this unit ball. And note that as you vary, so you can pull back, if you have your coordinate chart from this open set U, this coordinate neighborhood of the point P, you have this map, let's say phi, from U into the unit ball of Rn. You have the Riemannian metric on U. You can pull back the Riemannian metric on U to the unit ball on Rn via the pullback of the inverse of the coordinate map, namely phi inverse. Pull back this metric G restricted to U. You get an isometry, which gives you a metric on Rn. And of course, when you restrict the manifold to U, it's going to be isometric to, by definition of a literal construction, it's going to be isometric to this unit ball in Rn equipped with this equipped with a pullback of the metric on your manifold, pullback by the inverse of the coordinate. Okay. Now, the important thing is that this is now a metric on our end, and so we can kind of work with it in component form. It's going to be a symmetric in component form. It's going to be a symmetric, positive definite matrix, right? 1 tensor to 0 2 tensor, but you can express it as a matrix. And the important thing is that it has strictly positive eigenvalues. If you look at the spectral theorem, in fact, this because the matrix is symmetric, positive definite, right? It's a normal matrix, which means it commutes with the Hermitian conjugate. And so you can apply the spectral theorem and guarantee a unitary diagonalization of the matrix. And essentially, that means is that the eigenvalues of the matrix, you can find an orthonormal eigenbasis, and the eigenvalues are going to be strictly positive because because it's a positive definite um, tensor field, or yeah, it's a positive definite matrix. So the eigenvalues are going to be strictly positive. So in particular, as you vary your point in this ball of radius 1/2, this compact ball of radius 1/2, and the Euclidean space, since it's a compact set, the minimal eigenvalue of this metric, minimal eigenvalue is going to be realized at some point in this compact set. So you can create a lower bound away from 0 on the eigenvalues of your metric when you're restricted to this compact ball of radius 1/2. And so this allows you to bound the length of any curve. Let's say you have a curve in your original manifold. So you have a curve in your original manifold from P to Q. Due to the fact that the manifold is connected, by the way, we need the manifold to be path connected. The manifold must be path connected for any of this to make sense, because we need to be able to find a path from P to Q given two arbitrary points P and Q. All right. Now, that being said, I want you to let me know in the comments if a manifold is a Hausdorff second countable topological space, which is locally homeomorphic to Euclidean space. Are those axioms equivalent? Are those axioms sufficient to guarantee path connectedness if we assume that the manifold is connected in the traditional topological sense? Let me know in the comments for those of you who are into topology. But okay, so anyways, we have a path connected manifold. We can create, so let gamma be any curve from P to Q. We can construct a lower bound on the length of gamma. First, we have to use the triangle inequality. We're going to find the first point in our parametrization where this curve gamma intersects the edge of our coordinate neighborhood. And then we're going to map, and because this coordinate patch in the neighborhood U is an isometry because we've constructed it to be so by pulling back the metric via the inverse of the coordinate map. We can look at the image of the curve, which is, gamma, not gamma, but the piece of gamma, the first piece of gamma, starting at P and then ending at the edge of the coordinate neighborhood. We take that image into our unit ball. The image of that curve is going to have to pass through the sphere of radius 1/2, and so we're going to get a curve. We can bound this length of this curve below by, again, the piece of the curve which starts at the origin in Rn and hits the end point of the sphere of radius 1/2, and the length of that curve with respect to this pulled back metric is going to be bounded below by the radius of the ball multiplied by the square root of the eigenvalue, the minimal eigenvalue of the metric over the entire compact ball of radius 1/2. So this is a key idea, is that we can bound the eigenvalues of this pulled back metric below by some positive number, and so that allows us to bound and we can bound it away from 0 importing these. So that allows us to bound the arc length of any curve from P to Q below, using the constructor I just described, bounding it from below by a positive number, which this positive number only depends on the minimal eigenvalue of this pulled back metric over the compact ball of radius 1/2. So hopefully that makes sense. If that didn't make sense, please let me know in the comments. Because it's important. It's an important proof idea that Wang uses in these lecture 3 notes, and it's something to be aware about. We're essentially comparing the Riemannian metric locally to the Euclidean metric. We're saying that locally, this geodesic ball, consisting of all points within a certain distance from, and this is like philosophically we're saying is that this geodesic ball, consisting of all points, let's say of distance epsilon from a point P, with respect to this distance function we've just defined, variationally through the minimal arc length between 2 points of all curves connecting the 2 points. Yeah, we've compared this geodesic ball locally to the Euclidean ball. Okay, and that local comparison was provided by comparing the metric to the Euclidean metric, in particular bounding it on a compact region, bounding it below and above by the minimal and maximal eigenvalues. In this case, we used a lower bound on the minimal eigenvalue of this pulled back metric tensor over a compact region, but we can also use an upper bound as well in a different proof technique. Okay, and so let's keep going here. Okay, so right, so then there's an important note here. So if you have an isometry from a Riemannian manifold M to a Riemannian manifold N, and then if you look at the corresponding distance functions induced by the Riemannian metric, so let's say dm and dn, and then m comma dm is a metric space, n comma dn is a metric space. Turns out that this isometry is distance preserving. So if phi is our isometry from m to n, so recall that the isometry means that if you pull back the metric on n, you pull back the Riemannian metric on n via the map phi, then you get the Riemannian metric on M, and moreover, phi is a local diffeomorphism, and also has an inverse, has a smooth inverse. If it's an isometry, then it's actually not just a local diffeomorphism, but also a bijective map with a smooth inverse. Okay, so now the important theorem that was stated in these lecture notes is this theorem by Myers and Steenrod, which states that if MGM and NGN are two Riemannian manifolds with corresponding distance functions dm and dn, if we have a map var phi from m comma dm as a metric space into n comma dn, so just a map of the metric spaces, and our map var phi is surjective and distance preserving, in the sense that if P and Q are points in M, then the distance from P and Q is equal in M is equal to the distance from var phi of P to var phi of Q in N. If the map is surjective and distance preserving, then it is an isometry, and in particular, it is smooth. So it just gains a ton of structure if it's distance preserving and surjective. And in fact, there was a strengthening of this theorem by Palais to the following theorem, that the Riemannian distance of a Riemannian manifold determines its structure as a manifold, completely determines its structure as a manifold, the smooth structure, and its Riemannian metric. So the smooth structure of the manifold and its Riemannian metric are entirely determined by the Riemannian distance. Okay? Now, if you ask the question, given a metric d on a smooth manifold, is it true that d can be realized as the Riemannian distance for some Riemannian metric? The answer is no, you can consider um, there's many examples, but the example given in the lecture notes is the taxi cab metric on R2. So 2 points in this taxi cab metric can be connected by infinitely many shortest curves, whereas on a Riemannian manifold, locally near any point there is a neighborhood in which the point can be connected in which 2 points can be connected by a unique shortest curve. Okay, so that's an important um, kind of a local convexity statement about this arc length functional. Okay, so we're going to actually get uniqueness, local uniqueness of geodesic curves connecting 2 points in a Riemannian manifold. Now you can show um, using an argument that um, bounds that's a similar argument than as before, where we look at a neighborhood of a point, except this time we're gonna take a point, look at its neighborhood, look at a compact subregion of this neighborhood, coordinate chart to the unit ball, take the compact subregion, maps to the coordinate chart to the ball of radius 1/2, the closed ball of radius 1/2, which is compact, and then bound the eigenvalue of the metric above now, the pulled back metric into Rn. We bound the eigenvalues above. And using that fact, you can show that the distance function for any fixed point P, the distance function dist of dot comma P is continuous on it. Okay. So in particular, this distance function is going to generate a metric topology. That metric topology will coincide with the smooth structure topology on the manifold. And the important thing is that these metric balls in our new metric topology generated by this distance function, this dist f of dot is equal to dist dot comma p. So for every point P, we have a distance function on the manifold, um, then which is just given by the distance, the distance of whatever your input is to the point P. This distance function generates a metric topology, and the metric balls, okay, the metric balls of radius r, let's say, are, if r is small, if the radius of the metric ball is small, then they're locally Euclidean. They behave like Euclidean balls, okay? But if r is large, for a large radius, these metric balls may have a very complicated structure, okay? So, and in fact, okay, so this is an important additional note and an important example, okay? So what you can show is that, okay, you can ask about the smoothness of the distance function. Well, the distance function is definitely not smooth. It's continuous, definitely not smooth. Even in Euclidean space with the Euclidean metric, if you just look at the distance, it's not smooth at the distance of x comma dot is not smooth at x, right? It looks like a cone. If you graph it, it looks like a cone um, with the vertex of the cone at x. So it's not smooth at the point x, but one can show that in a punctured neighborhood of this point P, this distance of P comma dot function, this, I'll call it dist P, the distance from P function, in a punctured neighborhood of P, it is smooth. Okay, so you can find a punctured neighborhood where it is smooth, but it may have other singularities not at P, such as if you're looking at the sphere, if you look at the distance function on the sphere, okay? Again, this is Riemannian distance, so it must be induced by Riemannian metric, okay? If you look at any Riemannian distance on the sphere, okay, it's the sphere S2 is compact, and so it's going to have other singularities besides P. If you look at dist P on the sphere, let's say P is the North Pole, for example, and let's just do the round metric on the sphere. So this is the induced metric from the Euclidean metric. If we look at the round metric on the sphere, and then we look at the Riemannian distance that induces between 2 points, then it's just the arc length of the great circle connecting the 2 points, the shortest great circle connecting those 2 points. Then if you look at the distance, let's say P is the North Pole, then dist P has a singularity at the North Pole, but also at the South Pole, right? And in fact, for any compact Riemannian manifold, there you can find a point Q which is not equal to P, such that dist P is not smooth at Q. Okay, so you can always find a singularity away from the center of your distance function, or the origin of your distance function, whatever you want to call it. Now, this is another great comment made in these lecture notes, is that if you look at S2, and now let's just put a metric on S2. Let's not worry about its Riemannian structure. Let's ignore the Riemannian structure. Let's look at S2, the sphere, and let's just consider the Euclidean distance now. Okay. Well, the Euclidean distance is smooth at every point on the sphere except for the center. So like dist P, if P was the North Pole, then the Euclidean distance is smooth in away from P. It's smooth on the sphere minus P. Okay, so what that tells us is that since the sphere is a compact Riemannian manifold, in fact, the Euclidean distance on S2 is not a Riemannian distance for any Riemannian metric on S2. Okay? All right. Yeah, so that's... Oh yeah, the last little note here is that this dist P function is not just continuous, it's in fact Lipschitz continuous. Kind of, when we say Lipschitz continuous, like the definition of Lipschitz continuity uses the distance function itself. So it's kind of a direct consequence of the definition of Lipschitz continuity. Maybe, do y'all understand? Maybe the author of these lecture notes, Professor Wang, is talking about something more profound here. So, if any of you know about the Lipschitz continuity of this dist P function on the Riemannian manifold, please let me know in the comments. And otherwise, um, let's see if there's anything else I should mention. We can talk real quickly about the proof that the distance function is continuous, because I think that's kind of an important proof. So essentially, the proof of the continuity of the distance function, if you take a sequence in your manifold that converges with respect to the manifold topology. Let's say the sequence is a sequence A sub I, which converges to a point A on the manifold. And then we want to prove the sequential compactness characterization of the continuity of the distance function. Okay. So, the main idea is that we can construct curves from A to these A sub i's. So, yeah, we construct curves, a sequence of curves from the limit point A to these A sub i's, which we can do in local coordinates as long as we go far enough down the sequence such that we get close enough to A. We can then enter into local coordinates and build this sequence of curves. We can bound the lengths of these curves above now using this idea of pulling back, taking the coordinate chart of some neighborhood U of A into the open ball of radius 1 Euclidean space. Let's say the coordinate chart is phi. Pull back the metric G on U by phi inverse to get an induced metric on the Euclidean open ball of radius 1. Restrict that to the compact ball of radius 1/2, the closed ball of radius 1/2, sitting inside this ball, inside this unit ball. And then on that compact region, we can bound the induced metric. We can bound the eigenvalues of the induced metric above and below away from 0, and above by some positive constant. And if you want kind of a more rigorous proof of that, just look at the spectral theorem. I think I talked about that already in this video. But yeah, we can use the spectral theorem, bound the eigenvalues above and below And in particular, we want to bound them above, and then when we bound those eigenvalues above, it'll allow us to create an upper bound on the arc length of this sequence of curves. Remember, this sequence of curves is fixed. We're going to just choose them to be essentially straight lines. We're going to choose them to be straight lines in the chart map, and then whatever they end up being in the manifold itself is fine, because again, the chart map is going to be an isometry by definition, because we're pulling back the metric via the inverse of the chart map. So we choose these to be straight lines in the chart. We can bound the length of these straight lines in the chart above by this maximal eigenvalue over the compact ball of radius 1/2. And then this allows us to show that the lengths of these curves are going to 0, and so the distance between these 2 points is going to 0. Wait, is that? Oh yeah, the distance between the 2 points is going to 0, because you've created a sequence of curves connecting the limit point to the sequence of points. That sequence of curves has arc length going to 0, so the distance function, which is distance is bounded above by the arc length of any curve connecting the 2 points. The distance function goes to 0, and so that's enough to prove the continuity of the distance function. There is a slight side note of this, that a triangle inequality is used, in the sense that if we consider the function dist p, right, dist p, which is a distance function from p to some blank, like dist of p comma dot, then as a function, if we have a sequence of points, let's say a sub I, which converge to a point A, then we can use the triangle inequality, namely the reverse triangle inequality, namely the absolute value of dist p to AI minus dist p to A, absolute value, is less than or equal to dist A to AI. The argument that I just explained shows the distance from A to AI goes to 0, and so that tells you that dist P of AI converges to dist P of the dist P comma A. So the distance between P and the AIs converge to the distance between P and A. You get that using the reverse triangle inequality. That gives you the sequential continuity of the distance function, which is that's a key argument, key proof idea that I just want to kind of solidify in this video. Okay, yeah, I think that's it. Yeah, and then there's this important final corollary, that the metric topology on M induced by the metric dist coincides with the manifold topology on M. Okay, so the continuity of this function, this dist P function, implies that any metric open ball is also open in the manifold topology. Okay, by definition of continuity. And then, yeah, let me know if exercise to the viewer. Why? I mean, if you've gotten this far in the video, I'm pretty sure that you know that a continuous function, a characterization of a continuous function, is that the inverse image of open sets are open. But just a reminder. And then, so yeah, the continuity of the distance function implies that any metric open ball is also open in the manifold topology. And then if we have a manifold open neighborhood, we can shrink that manifold open neighborhood such that it is contained within this coordinate chart, which maps to this unit ball. And then again, we can find by bounding. Okay, how do we show that this topology coincides? We have to use a similar idea. So right, so we can. Sorry, one second. Just reading the proof here. Oh yeah, okay. So yeah. So basically by okay, so you take an open ball in the okay, so we've shown the continuity of the distance function implies that the inverse image of a metric ball is open in the manifold topology. Okay. Now now we just need to show that if we take an open ball in the manifold topology, we can find a metric ball inside of it. And in order to do that, we can take an open set of the manifold, shrink it to a coordinate chart, which maps into the unit ball, and then use this argument where we bound the eigenvalues of the metric restricted to this. I'm not sure if I agree with this argument actually. Okay, well the point is I don't know if I agree with the exact argument that's given in the notes entirely because they're not using compactness, but we essentially use a compactness argument of a ball of radius 1/2. So this coordinate chart bound the eigenvalues below away from 0, such that any point outside of this ball of radius 1/2, this closed ball of radius 1/2, any point outside of that ball must have a Riemannian distance which is greater than some fixed constant. And so that shows that the Riemannian metric ball of radius given by that fixed constant is contained inside sorry, I might have to crop this video. I might not crop it just because I don't really care. But what the heck? Oh yeah, okay, yeah. So any point outside of this, if you look at the sphere, okay, so the compact ball of radius 1/2. Any point outside of that compact ball must have Riemannian distance greater than some fixed constant, which depends on the minimal eigenvalue of the metric restricted to that ball. Which means that the metric ball of radius given by that fixed constant is contained inside of this unit ball of radius 1. And so yeah, that gives us that the topologies are equivalent. So the metric topology on M induced by the metric disk coincides with the manifold topology on M. Okay, I'm sorry for wasting some of your time in the last like 5 to 10 minutes of this video. My apologies. Have a nice day.